Hello, today we will learn about the conservation of energy in regards to how it is stored, energy approaches, two types of energy systems, what happens when friction or non-conservative forces are involved, and how power comes in the mix of it all. Chapter 7, we could see that there are three methods for storing energy: potential, kinetic, and internal. I like to imagine the meaning behind the three from a perspective of being on a roller coaster. When on a roller coaster, while the cart is going up on a slope or track, as it reaches the peak, the cart gains potential energy. When that cart goes down the peak, down over the peak, the potential energy is transferred to kinetic energy as the cart is moving, in which we could say that kinetic energy is associated with movement of a system. Internal energy is usually related to the temperature of a system, although when it comes to the roller coaster example, as the car moves up and down slopes consecutively, internal energy increases until the coaster cart comes to a halt. The two types of energy approaches that incorporate storing energy are the non-isolated systems and isolated systems. For non-isolated systems, it's possible for energy to cross a boundary of a given system, which results in changing total energy. These are seen more often than isolated systems in various branches of science, such as biology to engineering. For isolated systems, to say simply, it's inverse of non-isolated, as in energy cannot pass boundaries for a given system. For an isolated system, later on we will go over how conservation of mechanical energy can be used in this case. For non-isolated systems of energy, there are 6 total mechanisms of energy transfer possible to cross a boundary for a given system. The first can be expressed with the work-kinetic energy theorem, where energy is transferred by an applied force to the system, causing displacement, which is shown in the example of the man pushing the crate where friction is ignored. 5 other mechanisms of energy transfer are caused by mechanical waves, which is caused from a disturbance from airflow or another related medium. An example of that is ocean waves. Heat, driven by a temperature difference with the system and the surrounding environment, such as a metal spoon stirring hot soup. Matter transference through physical matter crossing the boundary of a system, such as pouring gas into a car. Electrical transmission, where a system has energy flow in or out via electrical currents, such as a phone charging. And electromagnetic radiation, where electromagnetic waves cross boundaries of a system, such as sun's energy directed on Earth by light from space. 6 of these mechanisms share a central feature in which energy is neither created nor destroyed, aka a conservation of energy. Conservation of energy can be shown mathematically through the change of energy of the system, E, is equal to the sum of the amount of energy transferred across the system, T. When including all of the mechanisms of energy, the formula is now expanded to change in kinetic energy, potential energy, and internal energy equal to work, heat, mechanical waves, matter transfer, electromagnetic transmission, and radiation. Now for isolated systems. Since energy cannot cross the boundary of a system, kinetic energy, potential energy, and internal energy are the only sources of energies involved, mathematically described as the change in kinetic energy, potential energy, and internal energy is equal to 0. Like previously mentioned before, if non-conservative forces act on an isolated system, the total amount of energy is conserved, although mechanical energy is not. Therefore, change in the energy of the system would be equal to 0. Example for an isolated system is a free-falling object, which is shown in the figure to the right. Given initial kinetic energy is 0, initial potential energy is equal to mass times gravity times the initial height, h, and the final kinetic energy is equal to 1/2 mvf squared, as well as the final potential energy, which is mass times gravity times any height represented by y, and that we know the change in kinetic energy plus the change in potential energy is equal to 0, we can expand that formula to solve for final velocity given in the final kinetic energy to determine the speed of the ball at any height y. When dealing with friction, work that is done is caused by a friction force made up of force and displacement. This can be shown through the sum of work of forces subtracted by friction multiplied by a distance and or displacement. In this case, it will be equal to kinetic energy. If work is done on a system by forces other than friction, then a non-isolated system is represented, in which the sum of work of forces is equal to work and equal to the change in kinetic energy plus internal energy. An example of this would be where a man pushes a car to a gas station. Since the car would be applying a force to the man, friction and a man's force would be applied to the car to balance out the force on the car, allowing the man to push the car. For mechanical energy changes dealing with non-conservative forces, there now is an additional source of energy rather than only kinetic and internal. Now there is potential energy. This change in potential energy added with change with kinetic energy is equal to both the negative kinetic friction and negative internal energy, which can be illustrated with the mathematical formula as shown. When combining that equation with the referenced equation from the previous slide, we result in an equation that represents the non-isolated system model that harnesses potential energy within which a non-conservative force acts. That is shown by the equation. Sum of work of other forces is equal to work and equal to the sum of change in kinetic energy, potential energy, and internal energy. To conclude this presentation, we could state how power is translated by work over time. With that definition, we can define instantaneous power and average power by manipulating time to change in time. In addition to that, according to James Watt and some simple conversions of work over time, we could see how 1 joule over second is equal to 1 watt of power, and how 746 watts specifically is equal to 1 horsepower based on the US customary system, which is important when considering performance outputs of a vehicle. Here is the end. Hope you guys enjoyed. Here are some examples of conservation of energy.